Lesson 28, we're talking scientific notation. Not sure how much you've been exposed to this yet, but scientific notation is really useful when you're dealing with super big and super small measurements. We'll talk super small, like width of a bacteria or something on a microscope slide. We'll talk that at a different lesson. Today we're focusing on large numbers. It could be useful for distance to the sun, right? In miles. That wouldn't be fun to try to write without scientific notation. Or maybe depth of the ocean in feet. That would not be very fun to do without scientific notation. The way scientific notation works is it's a number times 10 to a power. So maybe squared or something. What do we need for this number? Specifically, this number needs to be between 1 and 10. 1 and 9? 1 and 10, I suppose. 1 and 9 point something. You never want it to be 10. It needs to be less than 10 and more than 1, I think is what we usually say. So instead of 93, I would need to use 9.3 so that it's between 1 and 10. And if I have that squared, that's actually worth 930. The number 930 is the same as 9 and 3/10 times 10 to the second. If you typed in 10 to the second and then multiplied that by 9.3, you'd get back to 930. If I needed to go this direction, what I do is I look at 10 to the second, I move 2 spots, and then I do times 10 to the second. That's how you get to that. So let's break that down a little simpler looking at their examples, because that was a little bit maybe hard to follow. Scientific notation, again, is a method of writing a number as a decimal times the power of 10. For example, the speed of light is about 300,000 meters per second. That's a big number. In scientific notation, we can count how many zeros there are in that number. 1, 2, 3, 4, 5, 6, 7, 8. All right? Then we put the decimal here so that this first number is between 1 and 10. 3.0 now, which is 3, times how many zeros were there? 8. So we use an 8 for an exponent. And if I want to put this back so that it's not scientific notation, I would go 3 and then move that decimal 8 times. And I'd be back to 300 million. The first number, this 3.0, is called a coefficient. It's written with one non-zero digit to the left of the decimal point. The power of 10 is the multiplier that turns that coefficient into what it really is. Notice the exponent 8 that we had up here corresponds to the number of places that the decimal point shifted when the number is written into standard form. Okay? So you're going to have to get comfortable with going both directions using this. Example 1, Earth's distance from the sun is average 93 million miles. Huge number. How can we turn that into scientific notation so it's easier to digest? How do we get to this? The coefficient needs to be a digit to the left of the decimal. So 9. Not 93 because that's too big. 9. Decimal 3. That's simple. Because the rest are zeros. How many zeros? 1, 2, 3, 4, 5, 6. No. We don't count zeros in this case because this number right here, we're actually just counting how many times the decimal place moves. So if there's non-zero digits, we have to count those too. So I actually counted 1, 2, 3 zeros, 1, 2, 3 zeros, and then I counted the 3 to get a total of 7. But it looks different because you show the 3. You don't have to show these trailing zeros because they're not really going to change our value. So 9 and 3/10 times 10 to the 7th is the best answer for that. When Brigitte finished the 1,500 meter run, she announced that she had run 1.5 times 10 to the 6th millimeters, because millimeters are way too small to describe a 1,500 meter run. Write that in scientific notation. So we have to go from words now into scientific notation. 1.5 times 10 to the 6th millimeters. So I was just literally dictating it from what she said. Then put that into standard, is what we call the standard form, where it looks the way we normally are used to it looking with a lot of zeros. 1.5, right? And then how many times do I move this decimal in which direction? This is a positive exponent, which means we're getting bigger when we multiply. Going this way. How many times? 6 times. 1, 2, 3, 4, 5, 6. That's where the decimal is going to go, not here. And notice the 5 counted as one of my digits, and then the rest are zeros. 1 for each spot. Put your commas where they belong, and your answer will look like that. Feel free to read about the interesting information about some calculators and how they do scientific notation when numbers run out, the calculator runs out of room for the number. I'm going to do one more of these. Let's do letter D. 7.5 times 10 to the 8th means move the decimal to the right 8 times. Decimal's here. We're going to move this way. 7.5. 1, 2, 3, 4, 5, 6, 7, 8. My answer would have a 0 for each of these spots because it gave me no other values after the 5. Looks something like, count from the right to the left for commas, 750 million. I'd have to probably rewrite that without all the junk going on. Big number. That's why we did scientific notation. Let's try this one. 70,500. Okay, where would I put the decimal on this? I'm going to put it right here so that I just have 7. Not 70, not 705. It needs to be between 1 and 10. 7 times 10. How many times did I move the decimal to the left? When I put it there, I moved it 1, 2, 3, 4 spots. So I put a 4 there. Hopefully that's making some sense. Let's do A, C, E, G, H, and J. I want to get a lot of practice with turning it into scientific notation. That's probably the most valuable skill you're picking up today.